Okay, so integrating Markov processes with structural causal modeling enables counterfactual inference in complex systems. So there's a lot of buzzwords there. Has anybody here worked with structural equation models before? Okay, anybody work in computational biology, systems biology? All right, so we'll try and keep it really high level. Generally speaking, it's a practical framework for taking a specific kind of model, a Markov process model, that we're using to model complex systems and turning it into a causal model so we can do something called counterfactual inference. So this is a causal inference paper. And the examples are from systems biology, but could be applied to other similar types of complex systems. And finally, the impact with respect to this conference would be in reinforcement learning. So again, so let's go through these buzzwords again. A Markov process model, in systems biology, they tend to call it a stochastic kinetic model. What they do is they take a complex system, think of lots of random variables interacting dynamically in time. It's going to break up this system into such discrete random variables, it's going to, those interactions, it's going to model explicitly those interactions, and those interactions typically come from some kind of natural law. So for example, if you're modeling economics, you might come up with some law for how supply and demand interact. In biochemistry, you might think of enzyme kinetics or the ways transcription factors bind to genes. All of this is there's some kind of underlying physics there, and we're going to use that physics to probabilistically model these interactions in time. And so I say like causal models, but let's back up and say, what is a causal model? So a causal model, we're just going to call a model, a machine learning model, a generative model, a statistical model, any model that makes causality explicit and can model interventions. So that means if I change the underlying data generating process and I know what's going to happen if I make that change without actually observing the data from that change, I have a causal model. So like causal models, these Markov process models, because they have some natural laws that are kind of gluing them together, are used to predict the effects of interventions. So as a typical use case would be, as a modeler, I want to use a Markov process model to predict the post-equilibrium behavior of a system under an intervention. So you can imagine, like, if I introduce a new tax policy into a system of interacting agents, there's going to be a whole bunch of adjustments. That's the dynamics of the system, and then eventually there's going to be some equilibrium. I want to predict what that equilibrium is going to be. Similarly, if I'm doing drug discovery and I introduce some drug into a cell, and all the proteins in the cell are going to bump around a little while, and then finally it's going to hit some kind of new equilibrium, and I want to see, like, okay, did the protein that I want to express become expressed? So the goal of this is to kind of figure out interventions that are going to have a high utility, where utility is defined in terms of the domain. Say, for example, expressing some cancer protein. So a specific kind of causal model we're working with is called a structural causal model, abbreviated SCM. These are related to something you might have heard from economics or social science called structural equation models. They're more or less the same. What they do is they enable counterfactual prediction of a post-equilibrium intervention outcome. So that means that I observe some intervention outcome, and I say, all right, I have observed this. What would the outcome have been under a different intervention? So these types of you can't do that with every machine learning model. You can only do that with a subset of them. There's an algorithm that allows you to do that once you specify the model as a structural causal model. And so we want to be able to ask these kinds of counterfactual questions, especially in a reinforcement learning setting, for example, where you have some logged data and you say, like, okay, what would the data have given me if I had used, what would the policy have given me if I used a different model? Okay, and so, the issue is that these structural causal models, they typically lack the Markov process model's description of that natural law, that mechanism. The Markov process models themselves cannot, they use stochastic forward simulation to model interventions. This doesn't allow you to do that kind of counterfactual prediction. So what we contributed in this paper is an algorithm for taking the structural causal model, taking the Markov process model and converting it into a structural causal model in a way that maintains all the natural laws underpinning the original model, so that we can do counterfactual prediction in a way that is consistent with those natural laws. So in the paper, we applied this to two biological networks, these MAPK signaling pathway and the IGF signaling pathway, insulin growth factor pathway. These are models you can download from the internet. You can spin them up in MATLAB or Python, and then do sport simulation from them. So some of here's some of the results we have. So like what you see here, and the blue, the blue histograms here are the actual causal, causal effects, the counterfactual causal effects from the SCM model, and the a ground truth simulated causal effect from the Markov process model, and you see there's some overlap. The means are the same. The difference has to do, the difference in variation has to do with specifically the way that structural causal models model interventions. They use a Judea-Pearl's do-style ideal intervention. The ways you model interventions in kind of dynamic models have a lot more variance, but in the kind of supplement of our paper, we show how you can actually mimic that do-style Pearl intervention inside Markov process models as well. So an added advantage of this approach is that, so a big problem with Markov process models is what if your model is wrong? And usually it is, it's a complex system. So we showed that if you do counterfactual inference of interventions, use counterfactual inference to predict interventions, you make yourself a bit more robust to model misspecification, which means that even though your model is wrong, since you're conditioning on data, the prediction of the intervention outcome is still more right than it would be if you just forward simulated from your model. I'm at time, so the last thing I'll say is that we provided implementation in a PyTorch-based probabilistic programming language called Pyro. So this is a novel implementation of counterfactual reasoning using structural causal models in a probabilistic programming framework. And all the code is available on GitHub. Thank you.
Thank you for a great talk. Stephen Odaiwo here. A question I have is, so with the Markov models where you're modeling the mechanisms versus counterfactuals, in the counterfactual it sounds like you have sort of an inherent opportunity to compare models, if you will, and do some form of model selection that's inherent inside of the very structuring of the problem itself, if that's correct. Could you sort of get the same type of benefit using a Markov model by itself, but doing sensitivity analysis on the different parameters that are downstream inside of the signaling cascade?
Yeah, so even with the baseline Markov process model, because you're predicting interventions, you can always just predict an intervention, see what the outcome is, actually run that experiment in the case of systems biology, not in the case of economics maybe, but and then just see if the experiment falsifies your model or not. Right. So these models, because they're all models of intervention, you have some falsifiability built in.
Right, and that leads to my second question in terms of validation. What markers are you guys using downstream within the assay to measure and see which of these models are indeed correct or better, or more ideally a representation of what's going on inside of the cell?
So my experience has been that in terms of computational biology and you want to run a validation experiment, so it depends a lot on a domain. And of course, you need a noise model because obviously the thing that you're measuring in the assay and the thing that the variable that you're measuring in the assay and the variable that thing is tracking, there's a little bit of noise between there, so you need to add a little bit of make a noise model there. But I've had good experience with single cell data from, so I use systems biology, like proteomics examples, like single cell proteomic data. But if you're just looking at, say, the amount of one protein that you're interested in, then you can just have an assay targeting that protein, for example.
Cool. Thank you.
No worries.
Hi. So you mentioned that like the counterfactual inference is still robust to when the model is wrong. And I was just wondering, can you sort of talk about like how you determine that? Was it just like the empirical stuff you showed in the graph, or how does that work?
Yeah, so the intuition is that, so if say you make a model of reality and you start predicting interventions on that model, well, those interventions are exclusively a artifact generated by the model, whether or not your model is a correct model of reality. Now, with counterfactual reasoning, you're saying, conditional on what I've observed, what would have happened had I done a different intervention, right? So when you condition on an evidence, you're now feed this counterfactual algorithm is taking real world data as an input in that conditioning statement, right? And so you can think of it as like that real world data as anchoring the prediction to reality somewhat. Now, of course, it's still going to be sensitive to how correct or incorrect your model is, but it's going to have less of a problem than when you're just making predictions from a model that's not grounded in reality.
All right, thank you as well for an awesome talk. One of the elements in terms of what you've described is there may be multiple models that actually fit the data present. Mm-hmm. So the model selection piece is not just the question, but even if you've selected the right model that best fits the data, in this context, do you also explore multiple models or the option that multiple models may be valid?
So I'll put it this way, so our issue of causal modeling, of course, is that given observational data, there might be multiple intervention models that fit that data because that data maybe doesn't have an intervention or doesn't have all the interventions. Similarly, there's multiple counterfactual, so there's multiple, if I have a model that can capture counterfactuals, there could be multiple counterfactual distributions that are consistent with the same intervention distribution. And the counterfactuals are determined entirely from the structure of the model, and you cannot infer that from data. You cannot learn the physical structure of the model from data. You can only learn the distributions. And so this is kind of solving that model selection problem by saying like, okay, I'm going to pick of all the possible counterfactual models that can be applied to are consistent with this data, I'm going to pick one that captures the underlying natural laws that we believe from domain expertise are used that are present in this system. So you're selecting models that are consistent with your prior knowledge about the underlying physics of the system. But that again is also an assumption.